Alright, let's go ahead and pick up with our gas laws talking about stoichiometry. So one thing that I do want to remind you of is that an ideal gas is a hypothetical gas, but we can account for its behavior using the ideal gas law. So even though we don't really deal with hypothetical gases, the ideal gas law is still a really good approximation. So we're going to be using this to describe the behavior of all the gases that we encounter from here on out in this class. All right, so let's go back and recall what stoichiometry is looking at. So stoichiometry allows us to compare different molar amounts of maybe hydrogen to ammonia or hydrogen to nitrogen, but we're able to compare moles to moles. So remember that we can't compare mass to mass, we can't compare volume to volume. So now we're going to use the ideal gas law to solve for the moles, and then we can compare moles to moles for these things. So if we want to use the ideal gas law to maybe describe how much how much ammonia can be formed from, let's say 2 liters of hydrogen being stored at 284 Kelvin and a pressure of 8 atmospheres, we can do this because, again, we said that we can't compare volume to volume or mass to mass, but we can compare moles to moles. So if we look at the variables that we know the volume, we know the temperature, and we know the pressure. So we can use the ideal gas law, PV equals nRT, to solve for our moles of hydrogen. And then from there, we could just use a normal stoichiometry relationship. We'd say, okay, well, for every 3 moles of hydrogen, we have 2 moles of ammonia. And then you could solve for whether you're looking for mass, molecules, or atoms. If you're looking for a volume, now you can use the ideal gas law. So this is a really powerful tool that we now have at our disposal. Let's go ahead and look at an example. So for the deployment of airbags, what we'll see is that there's high temperature decomposition of the compound sodium azide. So we're going to see why this would be favorable to have in an airbag because we have this solid, which remember that solids are quite dense compared to gases. And whenever the solid decomposes, it produces a gas. So let's go ahead and use this balanced chemical equation here to describe this process. So for every 2 moles of sodium azide, whenever it undergoes high temperature decomposition, you can get 2 moles of sodium and 3 moles of nitrogen gas. Well, how are we going to figure out how much nitrogen gas can be produced? So we're given a mass of sodium azide. So we can't compare mass to mass. So we need to convert that from mass to moles. So what we're going to do here is we're going to start with our 45 grams of sodium azide. And then we need to convert that to moles. So the way we do that is we're going to divide by the molecular weight of sodium azide, which I believe is somewhere around 68.97 grams per mole. Alright, so we're able to convert from grams of sodium azide to moles of sodium azide. If we look at the rest of the information that's given in this problem, it tells us that the temperature is 30 degrees Celsius, there's a pressure of 1.15 atmospheres, and we need to figure out how many liters of nitrogen are generated. So if you were making a list of all the variables using the ideal gas law, so we have PV and then N and T because R is a constant. Well, what do we know? We know the pressure, We know the temperature. We're looking for the volume, so that means we had to calculate the moles. So we go ahead and solve for the moles, converting grams of sodium azide to moles, and then we'd have to do a stoichiometric conversion. So what we'd see is that for every 2 moles of sodium azide, there are 3 moles of nitrogen. So you'll plug and chug here really quick. And let's see. What do we get? Oh, we should get 1.04 moles of nitrogen. So now that we know our moles of nitrogen, we can rearrange the ideal gas law to solve for the volume. So remember, PV equals nRT. So rearranging this, we get V equals nRT over P. Here the moles was 1.04. R is that gas constant, 0.0821 liter atmospheres per mole Kelvin. And then the temperature, we have to convert this to our absolute scale. We can't use Celsius. So we're going to convert the 30 degrees Celsius to Kelvin. So 30 plus 273 gives you 303 Kelvin. And then we divide by the pressure, 1.15 atmospheres. And then hopefully we end up getting 22.5 liters. So think about that. We start with 45 grams of sodium azide, and whenever this decomposes, we end up generating 22.5 liters. So that's like 11 2-liter bottles of gas that's been generated. Think about that volume and how great that is. Okay, let's go ahead and look at a few more examples of stoichiometric conversions with gases. So there's an unknown gas bubbling up in a swamp. We collect the gas in a bulb, and what we end up finding is the density is 0.714 grams per liter. So notice that it's grams per liter, not grams per milliliter, like what we'd expect to see for metals or things like that. So it's grams per liter, so it's really, really a low density. Okay, so the density was measured at standard temperature and pressure. So we want to know what the molar mass of the gas is. So there's a couple things that we want to assume. Make it easy on yourself. So assume that you have a 1 liter sample. And by assuming that you have a 1 liter sample, you can use that density. And then that will tell us that the mass, well, I guess we need to multiply through by that 1 liter. So if we assume that we have a 1 liter sample, we multiply through and we have 0.714 grams of gas. All right. So if we want to find the molar mass of the gas so we can identify it, there's 2 things that we need for the molar mass. We need the mass and we need the moles, because remember, molar masses always have units of grams per mole. So what we're going to have to do is we are going to have to go ahead and go through and find the moles. So, well, let's see. What do we know? It says that we're at STP condition, so that's standard temperature. And for gases, that would be 273 K. And pressure would be 1 atmosphere. Okay, so we started out by assuming that we have 1 liter, so that's our volume. So we have PV equals nRT So we need to rearrange to solve for N. So N would be PV over RT. So plugging in, we should see that all of our units end up canceling out. We have 1 atmosphere times the volume of 1 liter divided by the gas constant, 0.0821 liter atmospheres per mole Kelvin, times the temperature, which is 273 K. Let me double check that this math is right. You get 0.0446 moles. All right, so now we know the moles and we know the mass. So what we can do is we can plug in that mass that we calculated, the 0.714 grams, divided by the moles, which was 0.0446 moles. And we see that the mass, the molecular weight here is 16 grams per mole. So if you were asked to identify this, possible formulas could include, let's see, if it's 16, I'd probably say that's CH4. Especially since it's coming from a swamp that someone's probably sitting in. So it's probably methane. So there's a couple of different ways that you can go through and solve this. I would go through the way that we just did and know that the density is equal to mass over volume. So density is mass over volume, and that the molecular weight is going to be your mass per moles, and go through and calculate it like that and just use some dimensional analysis. If you really like to memorize equations, we're going to derive really quick another way that you can memorize this or solve for this. So the first thing is, if we know the density of a gas, so we know that density is equal to mass over volume. Okay, well, let's think about what the ideal gas law is. So the ideal gas law is PV equals nRT. So we need to get volume in the denominator, but which one of these terms over on the right-hand side of the equation can be converted to mass? Well, temperature can't be converted to mass. R is the gas constant, so it's N. Well, how is N related to mass? Let's go ahead and rearrange this equation. So we'll have moles over volume equals P over RT. Okay, so now this is some sort of, I guess, molar density here. Let's go ahead and substitute in for moles. So we'll say, well, we know that moles is equal to the mass divided by the molecular weight, which we'll use the script M here really quick. So substituting in for N, we'll get the mass over the molecular weight times volume is equal to P over RT. If we multiply this molecular weight over to the other side, we'll have the density, which is equal to mass over volume, is equal to pressure times the molecular weight over RT. So this is another equation that you could use. Density is equal to pressure times the molecular weight over the gas constant times temperature. But I would probably just go through and use the gas law. and then go through and plug in with the density or molecular weight, whatever you're trying to solve for. So here's another problem that I would recommend that you try to solve on your own. Just, things to watch out for is always consider the units of R. So R has units of liters, atmosphere, per mole, Kelvin. So always consider those units on what R is before you start plugging into the ideal gas law. PV equals nRT. If there's information that's given with respect to the molar mass of something, even though it might not be written out in numerical form, you just make sure you're paying attention to the details. Here it's helium, so you might have to think about the molar mass of that. Let's go ahead and try to solve this on your own, and we'll go ahead and go on to determining a molecular formula. So here, this is going to be combining our knowledge of calculating empirical formulas and then molecular weights and molecular masses with the ideal gas law. So this is essentially two problems, and then we're going to combine our results. So the first one is we're given these percent compositions of carbon and hydrogen. Okay, so we haven't talked about naming things in organic chemistry yet. Otherwise, you would probably know what the formula for cyclopropane is. So we're going to have to do two different things here. We're going to have to go through and find the empirical formula. And then we're also going to have to go through and calculate something else. So here it tells us that we have 1.56 grams of cyclopropane. Then they give us a volume. They give us a pressure. And they give us a temperature. So what that means is if we know V, P, and T, using the ideal gas law, that means that we can solve for N. And if we solve for the moles here, so N is equal to PV over RT. If we solve for the moles, we can combine that with our knowledge of the mass and figure out the molecular weight. Then after we found the molecular weight, if we can find the empirical formula, then we will be able to determine what the molecular formula is. If we know the empirical weight and the molecular weight, we can figure out how many times that empirical formula goes into that base unit. So let's go ahead and set this up. So moles is equal to pressure, 0.984 atmospheres, times the volume, which is 1 liter, divided by R, times the temperature. So here this will be 323 Kelvin. Okay, so plugging this in, let's see what we get. Get 0.0371 moles. Okay, so if we wanted to from here, we could find the molecular weight of our compound. By taking our grams 1.56 grams divided by the mole. What we end up getting is a molecular weight of 42 grams per mole. Okay, so we're halfway there. Now what we need to do is figure out what the empirical formula is. So to do that, this is the percent to mass, mass to moles, divide by small, multiply to whole, that thing. So we have 85.7 grams of carbon. You're going to go through, convert that to moles. And then do the same thing with hydrogen. Assume you have 100 grams, so 14.3 grams of hydrogen. Divide by the molecular weight of hydrogen. And then what we end up getting is 7.14 moles of carbon, 14.03 moles of hydrogen. And we can see right here that this is about a 1 to 2 mole ratio. So our empirical formula is CH2. All right, so if you know the empirical formula, you can find the empirical weight of CH2. So carbon has a mass of 12.01 plus 2.02 from both hydrogens. So that ends up being a molecular weight of about 14. And I just rounded it off to 1 decimal place because that's what we calculated our molecular weight to be. So now the thing to do is to figure out how many times does this empirical weight go into the molecular weight. So you take your molecular weight, which is 42, divided by your empirical weight, and you get a factor of about 3. So that means you're going to multiply your empirical formula by 3. So your final formula should be C3H6, which propane is a 3-member carbon. Okay, so this looks like we're in good shape. So these are the types of problems that you guys will be calculating stoichiometry using. You might have to do a mole-to-mole ratio, just some other applications of the ideal gas law, factoring in the density or the molecular weight, and things like that. So that does it for this lecture. Next time what we'll do is we'll start to talk about partial pressure and Dalton's law, and then we'll also try to get into kinetic molecular theory.